I'm going to get started with the homework assignment. So what I'll do is I'm going to do the dry analysis type, approach. There are several ways to do it, but regardless of which way you do it, I'm hoping that you're learning more about the von Neumann architecture and also how these really simple assembly instructions work, because they are really a much simplified version of what we'll be dealing with later in this semester, like later today. Because we'll be using the XI386 instruction set. Well, a small subset of that, but they are much more powerful and kind of complicated in a way than these instructions. So what I'll do is I will go ahead and just analyze the program that is already written, and then from there, we'll talk about how to write the C code and and finish the whole process. Are there any questions before I get started with this? No questions? All right, so I'll just go ahead and get started here. The first instruction is take 50, and the way it works is it is just loading the content at location 50 into the accumulator. Okay? Now, how do we know, that the take instruction is just doing that? There are several ways to do it. The first way to do it is to look at the pseudocode, not pseudocode, the microcode corresponding to the take instruction. The take instruction starts with a 1, which means in the microcode table, what is the start location of the microcode?
0, 1, 0.
Yep, 10, location 10, because these are all in base 10. And even to date, I still cannot figure out why they're using base 10 and not base 2 or base 16. Okay, so the way it works is the take instruction will first initialize the accumulator to 0. It will put the INS to AB. It will take the least significant 3 digits into the address bus, and then it will use that to address the memory block, read it back into the data bus, and then it will do a plus. What the plus does is it will read whatever is on the data bus and add it to the accumulator. So the accumulator stores the sum of the two numbers. It will increment the program counter and then reset the microcode counter itself. So that means all it's doing is to read from location 50 and put it into the accumulator, because the accumulator was zeroed beforehand. Are we doing okay so far with the analysis of that instruction? Okay, so what I'll do is I'm going to use my text editor here. Oh, just missed it right there. And write that down. Okay, so we'll read location 50 into the accumulator. Okay, we'll just use A to represent the accumulator. The next instruction is add 50, add 50. What that will do is to read location 50 and add whatever is at location 50 to the accumulator. So we'll just write down the instruction here in English. Okay, so we add location 50 value to the accumulator. In other words, at this point, after the second instruction, it would have, the accumulator A would have twice the value of whatever is at location 50. Is that making any sense? Okay, because it loads it into the accumulator once, and then it will add itself to the accumulator. The third instruction is add 48. So it will add whatever is at location 48, which is what you need to report as the output of the program to the accumulator. Okay. And then we have line 4, the fourth instruction here. The fourth instruction is a save instruction. It takes whatever is in the accumulator and then put it back into memory location 48. So we basically store A to location 48. And then we have the next instruction here, TST. Now the TST instruction is a tricky one because this is the only way you can do conditional statements, quote-unquote conditional statements, within this instruction set. And the way it does the conditional statement is really kind of awkward from our perspective, because with any type of high-level programming language, and even with many architectures, they do not have instructions that work like this. This one is, I would say, it resembles more of instructions that are borrowed from Casio calculators in the 80s. Because if you look at Casio calculators in the 80s, they have programmable calculators, and one of the things they can do is just that, okay? Test something, and then depending on the result of the testing, is it yes or no, true or false, it can skip one instruction, and that's all it can do. In other words, you can choose to execute the instruction right next to it, or the instruction that is next to that instruction. Okay, so that's what it does. And last time we already demonstrated the use of that instruction. So what I will do here is I'm going to say I will use C code or pseudo C code here. I'm going to say, you know, if the value of location 49 is 0, then we'll go to a certain label, because if it is true, it skips the next instruction. So it will go to the location which is the halt instruction. And I'm going to use, you know, this halt instruction here, which is, you know, basically the same as, you know, exit 0 in the C program, because it's just, you know, stopping the entire thing. It stops working altogether. Is that okay? So the instruction that is right next to the test instruction is an unconditional jump, which is equivalent to a go to in C. So in this case, it's going to go to, let's say we go to a continuation label here, and the continuation label is down here. That is the effect of the test instruction. Okay, it only has the ability to skip one instruction or one memory location if the test is successful. If the test is not successful, then it will just do whatever most instructions do, which is continuing on with the following instruction. Are we doing okay so far with this code? Okay. So at the continuation point, which is equivalent to the increment instruction here, so this one is also kind of tricky, because, you know, the instruction itself is not very mysterious. Okay, all it does is to increment the value of location 0. But what is at location 0? It's the first thing that we are doing in this program. Read location 50 into A. In other words, it's modifying its own operand, you know, the operand of the first instruction, so that we are moving on to the next location. So that means, you know, when at this point, we'll have to say, you know, this location 50 here is not a constant. It gets changed by the program itself. Okay, so we'll basically, one way to change this is to say this is location X now, and before we use location X, we just say that X is initialized to 50. So now when we say increment the value of location 0, it is the same thing as saying X plus plus or plus plus X, whichever way you want to do it, because we are just incrementing that pointer by 1. Are we doing okay so far? How many people kind of notice this part when you're tracing through the program? Okay, good. You're not going to write any self-modifying program in this class, but I'm just going to throw this one out just to see whether you guys can observe that we are making changes to any instruction. Yep.
When did you also change the location?
The next one. Yep.
Yeah.
Mm-hmm. Well, the next one doesn't need any additional comment, because if you look at the next instruction, it is to increment the value of location 1, because it is an inc one, so it's incrementing the location of it's incrementing the value at location 1. But when you look back at the code here, that one used to be reading from location 50 as well. So if I'm incrementing this location and this location at exactly the same time, it's synchronized, then all I have to do is to change this to X. So we are adding the value of location X to A. And we are just using the same the same X. So that's why, you know, I can say, you know, already described by the increment of X here, because the increment of X from the previous line has already accomplished the same documentation. All right, so now we go to the next instruction. Let's see, where's the next one? The next one is to decrement location 49. Okay, so we decrement the value at location 49, and then we jump back to location 0. Okay, so we jump back to location 0, which forms a loop. Okay, so this is the beginning of a loop, and here we have a unconditional branch to the beginning of the entire loop, like that. It's just not wrapping around. I can turn on the auto wrap. Let's see here. There we go. Thanks.
And you need the value of 22.
The location 22 is
No,
a bug. that was
It's
not
location, it's
intended.
value. 22.
But since the value does not change at that location, so
Yeah.
you have to kind of put that value in. So you basically have to hard code. In this case, when you skip all the way to location 57, it has a constant of 22.
Yeah.
That was an accident. I just accidentally threw that value in, and the counter was not set up correctly.
Yeah, but
so
I did this.
Yep, you have to model that behavior as well because your code is supposed to
Yeah.
resemble the code of this program.
Yeah.
Yep. So then you have to say, location 50 starts with the least significant digit, L as the least significant digit of your student ID. And then you go all the way to 57, which has a constant of 22.
And it doesn't matter why you can write your student ID either way.
Your program should work for all student IDs, right?
Yeah.
Yep.
Is there a reason why you save every instance of the loop? Why don't you just technically store the accumulator and define saving that instance?
The accumulator get destroyed. But that's a very good question. Let me just repeat the questions for the sake of the recording and double check that I'm actually recording from the right channel because it will not be the first time that I record from the wrong channel. Nope, it's recording correctly. Okay, so to repeat your question, the question was, why can't we just use the accumulator to keep track of the counter? That's because as soon as we get to the first instruction, which is the read instruction, they call it something else. I cannot remember what they use it. They take. So as soon as we execute the take instruction, it's going to overwrite the content of the accumulator, which is a serious problem because we only have one register. And that's why we have to make sure that we store the result back into memory before we use the accumulator again. Okay, go ahead.
Can we just use add instead?
Can we just use add?
Yeah. Oh.
Yeah. To just do only adds and no take.
Yeah.
But then how would you get the number from the memory?
You still need a take. So you still need a take because the accumulator at that point has the value of location 49 because the test instruction also overrides the accumulator. Okay. Let's take a look. I mean, that would be an easy thing to check. The test instruction has a opcode of 6, so we skip all the way to location 60 in the microcode table. And you can see the test instruction definitely changes the accumulator. It does not zero it, but it reads the value into the accumulator. And that has to do with the only test you can do according to the picture is you can test for 0, but it can only be tested against the accumulator itself. So when you want to test whether a particular memory location has a value of 0, you have to load it into the accumulator first in order for that part of the circuit to activate. So that's why we have to store the result back and read it back every single time because we don't have enough registers or enough temporary storage in the ALU to store the intermediate results. So that's a good way. That's a very good point because it points out the limitation of a single accumulator and ALU because we can't really keep track of things in the accumulator. We have to keep writing things back to the memory and grabbing it back from memory. And as a result, the program is not efficient. All right. So getting back to the C code here, that's basically what it looks like. Okay, X is kind of like a pointer. Initially, it points to location 50, and then for each iteration of the loop at the end, it increments. Location 48 and 49, I did not write down here. Location 49 has an initial value of 7. It is a counter. And then location 48 has a initial value of 0. So those are kind of important as well. Are there any questions? Do you guys feel that? Yeah, go ahead.
I actually didn't use any pointer variables. Is that going to?
You do not need to use any pointer values. In fact, you don't even need to use 7 variables because you can read one value, use it, read one value, use it. So you just need one variable to store one digit of the student ID.
Yeah, I did an array of ends.
You don't even need an array if you do not want to go that route. The implementation is not important. You can use whatever implementation you feel comfortable with.
Okay.
Just modeling the behavior that matters.
Right, because I want you guys to analyze the assembly code and also potentially look into the microcode. That was the objective of this assignment. It was not to, it's not a competition for the most efficient or the most elegant way to implement the C version of this code. If you want to use like 7 variables, 1 for each digit, that's okay with me too.
I used 1,000 and just to have 1,000 lines in RAM.
You did?
Yeah, so I just mirrored like
Oh, okay.
line 48, I would use like integer 48.
Okay. So are there any other questions? Yep, go ahead.
CONTs continue, right?
Say again?
On number 8 and number 10 is like CONTs continue.
Continue is a label. I'm using pseudo C here, so that's just a label. For go to work, it needs a label to go to. So that's what it's called.
It's like go to.
The G word in structured programming.
And labels don't work with anything else, right?
Labels.
Sorry, labels don't work with anything else, right? Or do they? Just like something colon.
Yeah, something colon is a label.
But you can use that elsewhere. It's not just for go to.
That's a good question. I believe it can only be used in conjunction with a go to.
Okay.
A switch statement.
A switch statement, each case has a colon, but that colon has a different context. Yeah, not really labels. Not really a label. Because you have to say case blah 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 colon, so it's not really treated as a label. It's only treated as a value to compare to whatever is in the parentheses in the switch statement. All right. So do you guys want me to actually convert this into C code, or do you think this is already good? It's fine? Okay. So let's go ahead and move on then, because now we are done with the baby architecture. It's time to graduate to the i386 architecture. So we are going to get started with actual i386 type of programming. And it's going to take a little bit of time before we can have the first homework assignment, because it takes a little bit of time to build up enough instructions to do anything that's meaningful or semi-meaningful. So we are now moving on to the next topic. We are currently in topic 2. Well, we are actually still in topic 2. I think I just refreshed the page here. So we're going to start with the first link in topic 2 today, which is instruction addressing modes. Okay, so let's go ahead and take a quick look here. And this is the first instruction. We are going to talk about the mov instruction. Now, why that extra E is too much to type, I have no idea. You have to ask Intel engineer. Or maybe somebody just did not know how to spell move and decided it's mov. Jump is JMP instead of JUMP. Is that one extra U really going to kill you? No. But say again?
Depends on how many times you're writing it.
But there's no consistency of which letter is missing, because it's missing the last E of move, but it's missing the U in the middle of jump.
Yeah, but it's still 3 characters.
Yeah, but there's no consistency. I mean, you would say that
Only consistency is just 3 characters.
just 3 characters. Right.
It wouldn't say jump.
Why 3 characters? I mean, I can have almost an infinite number of letters per line. Okay, but anyway, that's just move. And then and then after this whole discussion of move, it's not even the right name for the instruction. It's not even the right name for the instruction. Let me just give you a really quick example of what move is about. Okay, I'm going to move this dry board eraser from here all the way to over there. Okay. What happened to the original location where the eraser was?
Not there anymore.
It's not there anymore, right? How do we move information or bit patterns in the computer?
Copy.
There's no such thing as move, right? I mean, you can copy, You can copy and then erase, but there's no such thing as actually moving. Okay? So the move instruction, the word move, is a misnomer. It is not a move instruction, it is a copy instruction. We are simply copying the content of the source to the destination. That's basically what we're doing.
So it's like a cut.
Hmm?
It's like cut.
Is it what?
Cut.
Cut and paste.
She's saying CAT.
Oh,
it's copy.
Yeah, like
Cop, COP, cop.
Yeah, I mean, because you get rid of whatever was there before after you do the copy.
But not in memory. In memory, if you have an instruction, okay, if you consider this statement, let's say x is an integer and y is an integer. I don't even care how they're initialized or how y is initialized. What is the result of this instruction? X ends up with the same value as y, right?
Yes.
Y still continue to have the same value as before. Whereas move kind of implies that, hey, where's my eraser here? It was here before. It's gone now.
So what is left out there? That's my question. Or the eraser used to be.
Because I only have one eraser.
Yeah. So is there anything in there? Garbage or?
The same value that was in there previously.
Oh, okay.
Yeah, because this is material, this is not. Yeah, so that's why it's a misnomer, because it's not. It doesn't reflect what the instruction actually does.
It's copy.
It's copy, assignment, that sort of thing, but definitely not moving. But that's how it's referred to by Intel engineers from the get-go, because I suspect this instruction was in the original 8085 instruction set, so it's not even recent. I mean, this is like way back in the late 60s, early 70s or so, probably.
And this is like AT&T style. It's not Intel.
Correct. Oh, is it not Intel? The
No,
8085?
Because BWL it's AT&T.
Yeah, right. But the instruction name itself is Intel. The MOV part is Intel. All right, so we'll talk about this meta syntax here of how to describe an instruction set. When you see something that is kind of boldface, MOV is actually supposed to be boldface, even though it doesn't look like it's boldface. It really is boldface. BWL is also boldface. Anything that's boldface, you have to type verbatim, which means the instruction starts with the letters MOV, and then when you see the square brackets, it means whatever is enclosed is optional. They can have 0 or 1 occurrence of whatever is enclosed. Now, when you see whatever is enclosed, let me just go highlight that portion. You can see it has B vertical bar W vertical bar L. That is a notation to say that these are alternatives. Choose one of these alternatives. So that means there are 4 variants of the move instruction just by this description. There's MOV by itself because the square bracket means optional. So you can do it without this, whatever is in the square bracket. The square brackets themselves is a part of the syntax description. It is not a part of what you need to include in your program. So the 4 variants are MOV by itself, MOVB, which means move byte, move word, or move long. I'm going to use this to represent an L just so that it doesn't look like a vertical bar. So those are the 4 variants of the move instruction. How many people have seen this type of meta syntax somewhere? Okay, and I think if you're into computer science, because you're in this class, I'm guessing that you're on your track to get a computer science transfer degree. Learning how to read meta syntax is very helpful, because this is actually consistent with a lot of different documentation standards to describe syntax. Now, what about SRC and dest? They're all in angle brackets. This means SRC and destination. These are tokens. In other words, they will be completely replaced by something else. Okay? They're tokens. They will be expanded or replaced by something completely different from what you see here. It's just a placeholder. Yep.
Move W what again? Move W what?
Word.
This is word, byte, and long. All right. So here we have a description of exactly what I just said. So that means, if you kind of forget what I said, it's okay. You can either replay the video or, just read the notes. And it's also consistent with most syntax description that people encounter in industry. Okay, let's talk about these two items here. This is the actual mnemonic. In other words, it's a somewhat easy to understand word that describes the operation. And then the other two are what we call operands. So source is an operand, destination is also an operand. They specify details so that the instruction can execute. In this case, one specifies where are we copying from, and the other one specifies where are we copying to. So those are extra information that we need for that particular mnemonic. If you want to translate this into C term, loosely, this is kind of like the name of a subroutine. This is the first parameter, and this is the second parameter. And in this case, the first parameter specifies where we are copying from, and the second parameter specifies where is the destination, where are we copying to. All right. Well, I think we just covered everything that we need to talk about regarding the instruction itself, the format of the instruction. So it seems like the move instruction is really easy to understand. So I don't really quite understand why this will take up an entire class. Yep.
Is that common part of the command?
Yeah, that's a common.
Do we have to enclose the?
Okay, hold on a second.
It's part of the command. It stays that whole block. So you'd say move. You'd say this, the
First operand, comma, second operand. Go ahead.
Enclose the source destination like both places or something?
No, we'll talk about it depends on the type of operand, which is our addressing node. And that's why, this topic, this particular slide really wants to talk about addressing nodes. But I cannot talk about addressing nodes unless I have an instruction to make it visible. Any other questions related to this slide here, the move instruction? Okay, looks pretty simple. Well, the mnemonic itself is really simple. It's the operands that can be a little bit difficult. The first operand is the immediate operand. In the way it looks like it's a dollar symbol.
It's like constant?
It's constant. Okay, but that's not how we like to see it in assembly language programming. Okay, let's take a look at the description here. The immediate operand, also called a constant operand in some contexts, is a bit pattern that is embedded into an instruction in machine code. As such, immediate operands do not use data memory at all, as all instructions should be in code memory already. Okay, so let's just kind of focus on this description here. All instructions eventually translate into a binary bit pattern. And the CPU will load that into the instruction register, just like in the Johnny program. And it will decode it, and it will grab different parts of the opcode to serve different purposes. Okay. In this case, what it means is you can have the instruction starting with some random bits, zeros and ones, to specify this is a move instruction. But the operand, immediate operand, is actually a part of the instruction itself. So if you're doing a move long, then it'll be 32 bits inside the instruction here to specify the immediate operand. Are we doing okay so far with that concept? And whatever these 32-bit specifies, the bit pattern, that becomes that particular operand. Can anyone kind of tell me which operand an immediate operand can fit into? The first one or the second one, or it can serve as either the source or the destination?
The source.
The source only.
Only.
Okay, the source only, because it's a constant. That's why you can only have an immediate operand as the source operand, but not as the destination operand. This can only be the first operand with a move instruction. Same thing with an add instruction, subtract instruction, because they all use the same format. Is that okay so far? Okay. All right. Furthermore, the value of an immediate operand cannot be changed in most situations, as it is very poor practice to modify instructions like the Johnny program that I gave you. a mystery program when a program executes. Self-modifying programs exist only for very specialized purposes, such as obfuscation. Okay, so if you want to look up how self-modifying code is used, you can look this up. Self-modifying code, Microsoft, because they actually use self-modifying code somewhere. Oh, it's not a. I think nobody has, or very few people have looked at this topic lately. In the earlier days, Microsoft used self-modifying code to help protect their software, so that people cannot easily bypass the first part of a program that checks certain things like copyright or whether it's a legit installation, the key and stuff like that. They use self-modifying code so that if you just dump out the object code of a program, you cannot just do a dry dock run like what I did to analyze what it's doing, because it will keep changing itself, and you cannot really easily predict what it will look like later on. But that's a really poor practice. It's not a good way to write programs. To use self-modifying code. Let's go back to this code here, or this description here. Operands, immediate operands are only used as a source operand. This is because an immediate operand cannot be changed. It is a part of the instruction itself, and we are not supposed to change instructions. And that's why it can only be the source operand, cannot be the destination operand. Any questions about this? Any questions? Okay. The access speed of immediate operand is really fast because it is a part of the instruction. So when you load the instruction into the instruction register, the whole thing is there already. So in order to make use of this operand, you're just making a copy or transferring a part of the instruction into one of the registers or into one of the pathways into the ALU, and that's really, really fast. All right, the next instruction, we need one more type of instruction to actually start to run some code. The next one is called register operand. This is a somewhat longer block here. Okay, a register operand is one that refers to the value of a particular register. The i386 has a few registers, not many. Let's see, where did I describe the registers? Let me see. Down here. Okay. I'm skipping around a little bit because I want to kind of give you a concrete example of the registers. You might want to remember this picture. I was too lazy to actually draw pictures and put it into the notes, but it's easy enough to do it here. Okay. So the question is, what is the width of a register of the i386 processor, which is a 32-bit processor?
32.
Okay. Any other numbers? I have 8, we have 32, and 16. You guys are all correct. You guys are all correct. Okay, so let's look at the 32-bit version first. Okay, so if you want to look at the 32-bit register, there's really not much to say, right? We have 32 bits. This is bit 0, and this is bit 31. We count bits from 0 because this digit represents how many 2 to the power of zeros do we have. And this digit represents how many 2 to the power of 31s do we have. So that's why we count it from bit 0 and not bit 1. Okay, so this is a 32-bit register. The next question is, okay, but what about the 16-bit registers? Well, as it turns out, this register, let's call this EAX here, which is one of the few 32-bit registers with this architecture. Okay, E stands for enhanced mode, and A stands for accumulator, X stands for extended, I think. Enhanced and extended accumulator, if you will. Okay. Now, if you just want to refer to the least significant 16-bit, there's a different name for that. So the entire thing is called EAX, but if you want to just look at the least significant 16 bits, this portion here, it has a different name. It's just AX. So it's accumulator extended, but not enhanced. Are we doing okay so far with this terminology? So sometimes when you want to refer to the entire 32-bit register, you call it UEAX. And if you want to only refer to the least significant 16-bit, you call it AX. Yes, sir?
Did you write 16 or 15?
That's 15.
Okay.
Because we count
You
from
said
0.
16, but I
Oh,
just
did I?
realized that you wrote 15.
Oh, okay. It's bit 15.
Yeah.
Okay. Any questions at this point?
Right.
So those are the exact same register.
They are exactly the same register.
Just
It's different
apart.
portals. It's
Yeah,
basically a
apart.
different view into the same register. So when you look at the entire thing, it's called EAX. When you just want the least significant 16-bit, it becomes AX. Now there's more to it, because you can also look into it just bit 0 to bit 7 for an 8-bit register.
AL.
Okay, this is called AL, and then it has a sibling, or it has a friend
AH.
called AH. So R goes from bit 8 to bit 15, and then L goes from bit 0 to bit 7. So this is the same register, okay? It is the same register, but it has 4 different names so that you can refer to the entire thing, the least significant 16-bit, the least significant 8-bit, or this kind of in between, bit 8 to bit 15 portion of it. Question? That was a hand. Yep.
What's the AH and AL stand for?
Accumulator low and accumulator high.
Okay. Is there a name for the outside of the AX?
For the,
Like the remaining part of the EAX? Like we have.
you mean this portion here?
Yeah.
That is a very good question. The question was, is there a way to refer to bit 16 to bit 31 of EAX? The answer is no. Yep. Good question. That's a very natural question. I wonder about the same thing, but no, there's no way to refer to just that portion of the 32-bit register. All right. So are there any questions about this? Well, this is a nice little scheme because it also works on EBX, ECX, and EDX. Same nomenclature. Okay, if you want to refer to the least significant 8-bit of, say, EDX, it is DL. But this is really not just A, B, C, D because they're alphabetical. A stands for accumulator, B stands for base, C stands for counter, and D, I think, stands for destination. So at one point of the evolution of this instruction set, these were all special purpose registers. They can only be used by certain instructions, but not general purpose registers where they can be used by most instructions. They are now the general purpose.
So will be enhanced and extended base?
Yep, enhanced, base,
Extended?
enhanced, base, extended, right?
Is it extended or extender?
Extended.
I think it's extended. Extended means it's 16-bit because the 8085 was a 8-bit architecture. So from 8-bit to, sorry?
Or 64-bit?
The 64-bit I think is Q. Is it starting with Q for quad?
Okay.
I mean, they could have just named these things, as A8, A16, A32, A64. That's a lot more scalable.
This is like AT&T style.
It's the same thing with AT&T. Yeah, you're right. This is this. So in Intel format, they don't refer to registers like these things.
Space, right? Okay.
I think
Okay, I'm just going to look up, this ancient thing here. All right, so we do have, all of these things here. They have accumulator A, B, C, D, E, HL, and HL is only used for indirect address. This is also shared by the Zilog Z80 processor, by the way. Let me see if they have the concept of register pairs, which we do not have in the i386 instruction set. So this is a fairly ancient, instruction set here. A is the 8-bit accumulator, and the other 6 can be used as independent byte register or da-da-da-da-da. Okay, so they don't really talk about the actual naming convention of these registers. which is okay. You know, that's not a big deal. Not too much. Yep.
You have BBX, NCX, and DDX. Are those also 32?
Yes, each one is a 32-bit register that can be chopped up like this one. In other words, this portion is the portion that can be A, B, C, or D. All right. Are there any questions about these 4 registers? They can be used in almost every single instruction. They're called general purpose registers.
Do we have like an AX with a EBX?
Yeah.
Okay.
So EBX has BX being the least significant 16-bit. It has BL being the least significant 8-bit, and a BH referring to bit 8 to bit 15 of the 32-bit
so instead of
register.
A, it's B for all that. Like
Right.
BX,
Yep.
BH, BL?
Yep.
Okay.
Same naming convention. All right. So that's the whole thing. We have other registers. We have ESI, EDI, which we do not use in this class. They're really the source and destination index registers for certain complex instructions. ESP and EBP, we do get to those registers later on in this semester. But for the time being, we are going to be only using EAX to EDX. Right, so we'll go ahead and take a look at some instructions. Okay, we'll actually get to start coding today, and it's a good idea to basically start our program. So let's go ahead and write a program. This is also a demonstration of the convention that you have to observe when you write code in assembly. Let me use GVim. That's not installed. Okay, Vim. I guess Vim is good enough. Yeah.
Can you increase the font size?
Absolutely. Let's see. I'll go ahead and use mousepad for that purpose. Okay, so this is mousepad. I can bump up the font size here. 17 point. Okay, that should be large enough, right? Okay, so let's go ahead and just write the program, and then I'll show you why it doesn't work. Okay, we'll have an instruction like this, and we'll just test the immediate operand. If you see a $ preceding something, that means it's an immediate operand. The $ denotes whatever is following is the value of an immediate operand. Okay, so we won't use anything too complicated. We'll just use a decimal value of 43, and we'll put it into a register because the second one cannot be an immediate operand. So we'll put it into a particular register. We'll just put it into EAX, the 32-bit register EAX. Now this is a valid instruction, but it's not a good one. Okay, personally, I would use only move B, move W, or move L, and make the width of the operation explicit. If it is left like that, which is implicit, L is the implied. Okay? In other words, if you don't specify the width of the operation, the default is 32-bit. But I personally would make sure that the instruction itself specifies the width of the operation, because if we get used to not doing that, later on we'll get bitten by this one big time. Okay, so always make sure that you specify this. Okay, so we just want to test one single instruction, but how do we stop the program? Well, but if we don't specify any additional instruction, it should stop automatically. Not quite. Okay, remember Johnny. If you look at a Johnny program here, if I don't put a halt instruction here to stop the program, it will just keep going. Okay, in other words, it's not like in C program where you have scopes. You have open curly brace and close curly brace in main, right? By the time you get to the close curly brace of the main function, it knows I'm done. Okay, and the main function is the starting point of your entire program. So when you're returning from the main function, you're basically saying this program is all done. So you don't really have to explicitly say, okay, this is the end of the entire program. It's time to exit. Is that right? What if you miss that return statement in main? And by the way, what is the return type of main? It is supposed to return an integer, right? If you miss a return statement when a subroutine is supposed to return a particular value, depending on the compiler and also which option you specify for the compiler, it can give you several results. One is no warning whatsoever. It's like, it's okay. Even though you promised me that you're going to give me a result, you're not giving me anything, it's still okay. Not a problem. Because even though you're not specifying a return value, you're still specifying a return value of unknown. Okay? It will return something. The caller will get something. It's just not something that you expect or you specify. So that's the first option. The second option is to turn on certain options of the GCC compiler where it will check. Okay? It will basically say, hey, you're supposed to return something here. How come you're not returning something? It will give you a warning. Or you can turn on the super nagging mode of GCC where it will consider that an error and you cannot go any further. It just won't let you compile the program if you don't play by the rules. Okay, but that's, with a C program in assembly, we don't have anything quite like that. So getting back to the source code here. So we need to terminate the program. We have to say, hey, this is the end of the program. It's time to get out of here. Okay, the way we do this, I'm not going to explain this at this point. We'll explain that later, okay? 0 into EBX, and the last instruction is int $0x80. Really? Lines, 3 to 5 is exit 0. It's equivalent to exit open paren 0 close paren in C and C++. Doesn't look like exit to you, does it? How can, moving two constants into two registers, and this really kind of weird, we're declaring an integer that has a value of 80 in hexadecimal. How does that have anything to do with getting out of the program?
It's not integer, is it?
It's not an integer, it's interrupt, it's software interrupt. We're causing a software interrupt at location 80 of the interrupt vector table, and that's the interface to talk to the operating system. We'll talk about all of these things later. For the time being, all you have to remember at this point is to say, well, I want every program that I write to terminate with these 3 instructions. Okay, that's okay for now. Okay, no big deal. We're not gonna, we won't need to explain that for the time being. All right, so let's go ahead and save this program and try to assemble it. And I'm gonna save it up to the root folder. Let's create a folder for today. And today is 2014 0218 cisp310. So find that folder. Right there. Okay. So I just call this test. Now, when you name a file in Linux, you can basically name it with any extension. The extension is, for the most part, meaningless at this point. Okay? When I run the assembler by hand, the extension means nothing. Okay? I can name this, .asm. I can name it whatever I want. The convention, however, is to name an assembly source file with a .s, lowercase s, as the extension. Okay? So we save it, save the file, go back to a DOS prompt, go to that folder, 2014-0218. Look at this, okay, we got the file here. So I'm gonna run the assembler. If you have done your first homework assignment, you might still remember the command to run and all the options to run the assembler. The assembler is as-gstabs-o test.o test.s. Okay, we have a problem here. The assembler comes back and comes up with a warning. End of file, not at end of the line, new line inserted. Well, that's really just a warning, because what happens is Mousepad is a lazy editor. It's a lazy editor because there's no new line here. If I insert a new line here and save the file again, that would take care of that problem. Woohoo, done. But my trouble is not over yet. The next step is to link it, okay? So right now we have what we call an object file. The linker is responsible to resolve all unresolved references to become an executable. So now we run LD, -o means I want to name the output file as follows. And then we give it the input file as test.o, which is the output of the assembler earlier. And it's complaining, once again, it's just a warning. It's just saying, hey, I cannot find the entry symbol _start. I'm defaulting to this location. In other words, when you write a program in assembly, you have to indicate the starting point of the entire program with a label. If you don't, then it will assume the first location of the first object file is the starting point of the program. In this case, it really is, okay, so it's going to work, but in general, that is not the case. So I'm not going to leave the program the way it is with all these warnings, right? So I'm going to go back to my source code here just to fix this up here. The first thing I will do is to say .global _ start. .global in this context is kind of like extern in C. It is basically saying the following label may be defined by somebody else in another file, or if it is defined by me, I want to make this visible to the linker. Are we doing okay so far with the meaning of .global? It simply means the use of this label is not limited to this file. Somebody else may need to know this label as well. Okay. And then the next thing we do is to say .text. .text is a switch. There are two segments that the assembler can natively keep track of. One is the data segment where you put all your global variables, and one is the .text segment, which is really code, which is where the instructions belong. So .text is telling the assembler, hey, make use of the instruction or the code segment and not the data segment. And now we can start the label _start : which is defining the starting point of the entire program. Now, without these 3 lines, the program I can run the program just fine. But with these 3 lines, it is much more compliant, and we won't have problems later on. Are there any questions at this point? So for the time being, you just have to remember, just for the sake of bookkeeping, these 3 lines are necessary, followed by your own code, and then these 3 lines specify that we want to get out of the execution of this program. So that's the general format of a program, at least for the time being. So let me save it again. Go back to the command line, rerun the assembler. Exclamation point means look up in the history of this particular command line interface and locate the first command, the most recent command that starts with AS. Same thing with LD. And this time nothing got complained, and we have an executable. The executable is test, the object file is test.o, and then the source file is test.s. So it's time to run the program. Okay, when you run the program by itself, you have to say ./test and not just test. The reason why you have to precede the name of the program or the executable with / is because dot means the current folder, but the current folder is not specified as a part of the path, which is what the bash or the shell looks for the commands. So that's why you have to precede it with a dot. You basically say, don't look any further, it is right here in this folder. A / is only used as a separator between components in a path. So it's basically literally saying, in this folder, the file called test is what I want to run. So here I'm running the program. Obviously, it doesn't do a single thing, but it doesn't, do a segmentation fault either. So it's okay. It's a very neutral program. It doesn't do anything. So what is the whole point of doing this? I mean, don't we want to kind of look into the execution of this program and see what happens to the register and stuff like that? Yeah, let's do that. We use GDB for that purpose, which stands for GNU Debugger. This is also the same debugger behind Dev C++ and code blocks. So if you are used to that type of program or IDEs, these are all the back-end tools of that particular IDE, of those 2 IDEs. So when you use GDB, you just say GDB test without the /. Having the / doesn't hurt, but it's not necessary. All right, and Now GDB is ready because you can see the prompt, in GDB in parentheses. That's the prompt in GDB. In other words, we are no longer in the shell in the command line interface. We're now inside the debugger itself. Unlike in code blocks or dev C++, there's no such thing as double-clicking, right-clicking, and that sort of thing. You have to interact with GDB using command line commands. Are we doing okay so far? And the very first command you need to learn is help. Because you will need to refer to the manual from time to time. And because there are so many different commands in GDB, they are all organized in these categories. Okay, so you can say help data, you can say help running, and so on and so forth. So each one is a subcategory with its own list of commands under that. Okay, but you don't have to look through this unless you really want to, because I will go through some of the commands that you will most likely have to use anyway. All right, so the first thing we want to do is to set up a breakpoint. Now, if you want to, you can say help breakpoint, and it will tell you all the commands related to setting breakpoints and so on. And you can definitely see that there's really quite a lot of stuff. So you don't really want to have to go through all this list here. I'm telling you that you can say break just by using the B symbol. Okay, B is the abbreviation of setting a breakpoint. There are several ways to set a breakpoint. You can set a breakpoint based on location or based on the line number of that particular instruction. So you can do it either way. In this case, I want to specify the line number, or you can use a label. So this is on line 4. The instruction I want to stop at is on line 4. So I'm going to go back here and say B4, which stands for put a breakpoint on line 4 of the source code. Now, if you don't have the editor open at the same time, can I take a look at the source code in the debugger? The answer is yes. You can use L for list, and it can show you the program starting from line 1. But if you press L again, or just press the enter key, if I do L again, it would say I'm already at the end of this program, because every time you type L, it will continue the listing from the previous time. Now, the only way to rewind that is to specify the line number again. Then it will start from the line that you want to list. Are we doing okay so far? All right. So I need to set a breakpoint on line 4. So B4 is setting a breakpoint. And now I'm ready to run the program. To run the program is R for run. And now it stops on line 4. Because GDB says, okay, we are starting to run the program, but now we're hitting breakpoint 1. And the location is on test.s line 4. This means we are about to execute the instruction on line 4. We have not executed the instruction on line 4 just yet. Are we doing okay so far? Anna? Okay. So now that we're about to execute this instruction, I want to do a few things. Well, at least one. I want to take a look at the current content of register EAX. So IREAX is one way to look at the content of EAX. And it shows you in two ways. It shows you the value in hexadecimal as well as in decimal. Because sometimes if you're doing calculation, it might be more handy to look at it from the decimal perspective. Other times, if you want to look at a bit pattern, hexadecimal is more friendly from that perspective. But it gives you both at the same time. Are we still doing okay so far with the debugger, or how to use the debugger?
What's IR stand for?
IR stands for info or information register. But you need a space in between here because they are actually an abbreviation of two words. All right, so now that we know EAX started off with a value of 0 before the instruction, let's go ahead and continue the execution of the program. Now, if you want to continue the execution of a program, C is one way to do it. But if you use the command C, which stands for continue, it will continue the execution at full speed, which means it will run all the way to the end, and you won't be able to catch it and say, but hold on a second, I just want to run one single instruction. If you want to run one single instruction, it's called stepping. and you can abbreviate it with just the first letter of the word. So S, enter. Okay, now it's ready to execute line 6, which means it is done with the instruction of line 4. Let's take a look at the register again, EAX, and it now has a value of 43. Kind of as what we would expect. Are there any questions about running GDB? What's the IR again for? IR? Info register.
What are they doing again?
Say
What are
again?
they doing again? What are they doing?
What is it doing? It shows you the content of that register. Or, if you prefer to have more detail, just say help. It's very terse, but it does describe what it is. All right, so are we okay with the debugger at this point?
If you read infrared instead of IR,
It will do the okay. You can say info register is do the same.
So you could instead put that to like the AL or AH also? If you were to change
That I am not sure. That is a good question. I have never done anything like that before. So yes, it can refer to AL, AH. Okay, here's a quick question. What do you think AH is going to display?
0.
0. That's right. Because 43 only have to make use of bit 0 to bit 4. Okay, so bit 0 to bit 4. It has to use a bit 4 because it's greater than or equal to 32. But this register, which is the high register AH, is going from bit 8 to bit 15. They should all be zeros. But let's double check, confirm that. Yep, sure enough. All right, good questions. Any other questions at this point? Yep.
If you store the value in AH, what would AL be?
If you use an instruction to only store something into AL, it does not affect what AH already has,
I mean,
or the rest of the register.
What if there's overflow? What if it's higher than an 8-bit?
It
You try and
still.
store it in AL.
That's a very good question. Okay, so the question is, what if you're storing something that cannot be stored in 8-bit? It requires more than 8 bits to store, and yet you specify the destination to be a 8-bit register. That's your question, right?
Yeah.
The assembler would actually complain, but it only reports that as a warning, not as an error.
Would it overflow and
No, it just truncates. It only pay attention to the least significant 8-bit.
Okay.
So the remaining portion it just kind of ignores, which is really annoying because it should have made it an error, so that the program just would not compile or would not assemble, and forces you to take a look at the situation.
If you type in just IR, will it list all of the registers?
Yes, if you type in IR and then the return, it will look at all the registers, which is kind of handy if that is what you want, but it can also be confusing, and it takes up a lot of screen space because you might not want your screen to scroll up by that many lines if you want to kind of trace your program and only pay attention to 1 or 2 registers. But you can see that it has a whole bunch of registers. I think there's a total of about 16 of these. And some are extended registers that are not in the original architecture, not in the 8086 architecture. Okay. Any questions at this point? No questions? Okay, if there are no questions, then we are going to move forward to the next addressing mode. Okay, this is one addressing mode. It's the register addressing mode. So we're going to go back up again, and then we'll take a look at something that is really confusing. It's called a direct addressing mode. Okay, in the Intel terminology, it's called a direct addressing mode. A direct operand specifies an address, and it specifies an address, and the value at that address is the value of the operand. Now, this statement by itself, this sentence by itself, requires a little bit more time to kind of digest what does it actually mean. The address is specified as a part of the instruction. But that part of the instruction is not the value of the operand. The value of the operand is the content at that location. Okay? Is that okay so far? Let me give you an example. So the example is an instruction like this. Okay? So let's say the instruction is move L. Okay, so we are moving 32-bit. The first one is an immediate operand. We'll make that hexadecimal 23. And the next one is a direct operand. And we want to make the direct operand something completely different from this one. So we'll just make that 0xABCD. Okay? Okay. With a $sign, it's an immediate operand. Without a $sign, it is a direct operand. An immediate operand does not access memory. A direct operand accesses memory.
What is percent sign?
Sorry?
Is percent sign?
No. This is 0x, which is just hexadecimal.
You access registers with percent sign.
That is correct. With registers, you use the percent symbol before the name of the register, but these are not register operands. Okay. So I want to show you what it looks like, in terms of the actual opcode. Now, a part of the opcode, at least the first part here, specifies the instruction itself, which is move L here. Obviously, I cannot remember, the actual opcode, which is a binary. Now, the other portion, the rest of this, is now divided into two chunks of 32 bits. Okay? I'm going to make the assumption that this part here corresponds to the source, and this part corresponds to the destination. The source part is going to be 23 in hexadecimal, but expressed as a binary number. Okay? So we have basically a whole bunch of zeros because we have 24 zeros to begin with, and then the binary bit pattern representing 23 to go into here. Are we doing okay so far? Can someone do the conversion real quick? What is 23 in hexadecimal represented as binary? 0011 as 3, 0010 as 2. So that's the binary bit pattern for 23. And then we just have a whole bunch of zeros on the other side to make up 32 bits for this operand.
What was you mentioned that with the $sign was the immediate operand?
With the $sign, it is immediate.
What was it without?
Without it's direct. Okay. What about the other one? What is the big pattern of ABCD in hexadecimal? D is 1101, C is 1100, B is 1011, and A is 1010, and then another whole bunch of zeros to the left-hand side, to the more significant side. Well, there are only 16 of these things, okay? So after you work with these things for a while, you remember, how to look up, from hexadecimal to binary and also the other way around. The nice thing about this, okay, I know most of you guys are kind of thinking, how can I know, how to convert this to this so quickly? It's just a link table lookup. There's no trick to it. 0, 1, 2, 3, 4, all the way, and then 9, A, B, C, D, E, F. And then on the other side, you have the bit pattern. 0, 0, 0, 0, 0, 0, 0, 1, da 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 da. 9 is 1, 0, 0, 1 in binary. A is 1010, and so on. The last one is going to be F in hexadecimal, and in binary it is 1111. It's a one-to-one correspondence. No division, no multiplication. All you have to do is to say, for one digit in hexadecimal, we have 4 digits in binary. And also the other way around. If you want to go from binary back to hexadecimal, you just have to chop it by 4 and then look it up. Yep.
So the max is 8 or 7 hex digits.
Say again.
The max you can put in there is 8 or 7 digits in hex.
8. Yep. 8 hexadecimal digits corresponding to 32 bits. Because one hexadecimal digit represents 4 bits.
So there's 16 different combinations in the core code. Okay. So in the binary, there's 16 different combinations. That's why it's 0 through 9. Okay.
That is correct. Because you have 2
different combinations. All
right. 2 to the power 4 is 16.
Right.
All right. So now we have 2. I mean, this is really just a I just want to do all the conversions into binary so that you can actually see that a part of the instruction, this part here, is this bit pattern, and this part of the instruction, the actual instruction, would be these 32-bit. Okay? So now the question is, what is the operation? What are we doing with these bit patterns? The first one is easy. It's an immediate operand. So that means these 32 bits actually specifies the value of the first operand. That's the easy one. Okay, we got a handle on that one already. What about these? This particular bit pattern. I mean, we're not going to overwrite this instruction, a part of the instruction here. That's not the objective of a direct operand. What we're going to do is we will take a look at these 32-bit, which is just a number, right? We use it as an address. Okay, we go to the location specified by this bit pattern, treat it as an address, and then we overwrite the 4 bytes starting at that location. That is what a direct operand does. In other words, a bit pattern that is a part of the instruction specifies an address. The actual value that we want to access is at whatever is at that location. Are we doing okay so far? The difference between an immediate operand and a direct operand. Okay. So when you look at this instruction here, the result of this instruction is an attempt to overwrite the 4 bytes starting at location 0, which means we are overwriting location 0, 1, 2, and 3 with the content of all zeros. That's what that instruction will attempt to do. Now remember, why do you think that I said attempt? Because location 0 does not belong to your application. In other words, as far as the operating system is concerned, you are trying to access a location that is not yours. And what do you think will be the result of that? Well, it depends on the operating system. In DOS or Windows 98, yeah, you can go ahead, you can overwrite whatever you want. In any type of operating system that operates in protected mode, you try to overwrite a location that you're not supposed to, it will cause you a GPF in Windows, and in Linux is segmentation fault. Exactly. They mean exactly the same thing. Okay. Some of you may not believe that, okay, and say, well, I think this instruction can crash the operating system. Well, let's go ahead and give it a try. So we'll go ahead and write the second program. And I'm going to use this editor here, start new, and I'm going to be a little bit lazy. Oh, okay, it has tabs. Nice. Copy, paste, save. And we'll just call that direct because it illustrates what direct operand is.
That's not laziness, that's efficiency.
Oh, copy and pasting?
Yeah.
I could have used pound include also, but. Okay, so we'll go ahead and overwrite location 0 using the constant 0 to do it. Okay, make sure we save the program before we assemble it. Okay, let me just put this one aside so you can see the actual code. Assemble -G steps. G steps actually stands for keeping the debugger symbol table. Okay, because this is the only way that the debugger can associate a location of your memory of your program to the line number of the source code. Okay, so that's basically what it is. If you forget this particular option, it will still assemble, not a problem. It will still link without a problem. But when you get into GDB, it would not know which source file to look up, and it would not know which address in your program corresponds to which line in the source code. -O means specify the output file with the following name. So we'll just call this direct.o. Direct.s is the name of the source file. Linker, same thing. -O specifies the name of the output file, and then we give it one single input file as the object file. And once again, it doesn't make sense to run the program directly. We'll have to go through GDB to see its results. Actually, no, well, let's go ahead and do it first without using GDB. segmentation fault, as expected. Okay. Well, what if we do it in assembly? Now, if you're trying to write your program as a homework assignment, and your program, you try to run it without GDB, it gives you a segmentation fault, what are you going to do next? Segmentation fault doesn't tell you which line is offending, which instruction is offending. It simply says somewhere in your program is trying to access a memory location that is outside of what is allocated to your program. Doesn't tell you anything. So what you really want to do is run it in GDB.
Like step by step?
Well, you can do it step by step. For certain things like what we have here, if you just run it even at full speed, it will tell you that the segmentation fault is coming from line 4 of this program and is coming from this specific instruction. So it's already giving you tons of information because it tells you which instruction is the problem, and now you know, oh, okay, this instruction is the problematic one. What is wrong with it? But this instruction can be one of like a few hundred lines of code, so this gives you, a lot more information than just running the program and see what it does. Do we have any questions at this point? Okay. If
Is there a way to know like which parts of memory belong to be in the program?
You have to do the allocation, and that's why we have the .data segment. So we'll go ahead and finish that part of the program so that we can actually move something into memory location and verify that. Okay. So we have 3 minutes remaining, and that's enough time to do this. Okay. So now what we want to do is, before we specify the program, we'll use .data to tell the assembler, hey, I want to switch to the data segment. The data segment versus the code segment, you can look at it as two binders. One binder is responsible to store all your variables. The other binder is responsible to store all the instructions. .data means use the data binder. .text means use the code binder. So you can only use one at a time, and you can use these directives to switch which one you're using. So I'm going to switch to this one first, and all I want to do is to say, I want to allocate 4 bytes, okay, in the data segment, and so that I can store something into that location. Okay. So what I'll do is I'm going to label it X here. X colon, means I'm defining a label X, and I will say, .int 0. When you use .int 0, is telling the assembler two things. One is allocate 4 bytes. Okay, give me 4 bytes from the data binder. And the second thing is to initialize these 4 bytes to represent 0 as a number. Are we doing okay so far with that directive? .int is going to allocate 4 bytes and initialize the content of those 4 bytes to the value of 0.
Is there a way to put comments?
Comments?
Yeah, I was just
Yes.
going to ask about that.
If you want to add comments to a program, you put a pound sign. Whatever is to the right-hand side of the pound sign is ignored by the assembler. Okay, so in this case, we can say we are allocate 4 bytes, initialize to 0 to a 32-bit 0. There you go. And also, use X as a label for the first location of these 4 bytes. So we'll go ahead and save it. And we'll go ahead and change the instruction here so that instead of writing to location 0, we'll try to go to location X. And also let's pick a different bit pattern here. Let's pick something a little bit more easy to spot. Okay, we'll do 1, 2, 3, 4, A, B, C, D. Okay. Are we ready to start? Okay. So we'll go ahead and save the program. This X is referring to this X here. In other words, the value of the label is used here, which turns out to be the address of those 4 bytes that we allocated. Okay. So we'll go ahead and switch to the command line.
Do you need a space after the colon or not?
Say again?
Do you need a space after the colon?
Nope.
No.
You mean the colon or the comma?
No, the colon on the line 6.
Yeah, you don't need a space.
Okay.
Yep. All right, so with assemble. Okay, keeps complaining. Okay, what is it complaining? error junk ABCD of the expression on line 6. Oh, okay, I forgot the 0x prefix. All right. What kind of assembler is this? It could not read my mind. All right, so the first thing is, if you run the program by itself, it's not going to segmentation fault anymore. But when you use GDB, we can also run the program. But how do we know, what is the content at those locations? That becomes the problem, right? So let's go ahead and put a breakpoint on line 6 now, and no simple table. Oh, I just used GDB without the name of the executable. Okay, never mind. Okay, we're running the program. We're about to execute this execute this instruction. So we have two things to do. Okay, we want to take a look at the 4 bytes at location X right now, just to see what it is at this point. Then we execute the instruction, and then we check again. That's the only way we can double check and make sure that the instruction does what it is supposed to do. There are several ways to do this. The first way to do it, which I think is the most general way to do it, is to use the X command. The X command, I'm just using the help here. The help is very terse. It just says X/format, and then you specify the address. So the address is just an address of a memory location. In this case, you can use X, because X is the label of that location. The format part is kind of the interesting part, because you can specify with how many bytes do I want to look at, and then you can also specify what base do you want to print those values in. Okay, so let's go ahead and I would use since I already know the command. The first part is W. If you want to use 32-bit in the debugger, W is the word. But when you specify W as a part of a move instruction, it means 16-bit. Okay, so you got to keep that in mind. Okay, it's not the same thing.
Did they disagree on one?
Huh?
Did they disagree on what it should be?
It has to do with the debugger has to work with all versions of compilers, regardless of the architecture, and then the assembler is specific to the i386 architecture. Yep.
So I just want to confirm, the X is specifically referring to the X in our program, and it's not.
Not this X here. Not this X.
Okay.
This is the command. The X here is the name of the command, which stands for examine.
Okay.
And then the slash separates the command from the format. W specifies the width, 32-bit, and then the second X specifies hexadecimal. And then the third X specifies the location, which is actually our label X here.
What was all the X?
Okay, the first one is examine, which is the name of the command. The second one is hexadecimal. We're printing in base 16. And then the third one is the location, which is the name of the label that we want to examine. All right, so let's take a look. And it says cannot add access memory at location 0 because it's actually doing one indirect already. So the way to do it is to use an ampersand. Okay, I know it's kind of awkward. We'll talk about this a little bit later. Okay, so it's 0 at this point. Single step through the instruction. Okay, make a breakpoint on line 6. I didn't make a breakpoint already. We're at the breakpoint. Single step. Take a look at that location again, and it is 1, 2, 3, 4 A, B, C, D in hexadecimal. So the move instruction did what it is supposed to. Are we doing okay so far with the debugger?
Why is the X/WX?
The first X is examine. The W means I want 32-bit. Print out 32-bit. Or examine 32 bits. The second X is hexadecimal. And then the ampersand X is the location of what I want to print. Oh yeah, absolutely. I think binary has a is a T instead of a X. So now it's in binary. You can do it in octal. You can do it as an integer. Now, if you do it as an integer, there are two options. Because when you do it as an integer in base 10, you can look at it as a signed number and also as an unsigned number. In this case, it doesn't matter because the signed is 0. But you can use the E for signed, and then use mu for unsigned decimal.
Yeah, that's your answer.
After that, it's the location. You can use 0, 0. You can actually write down the actual number if you know the location. But since I'm using the label in this case,
You're still here, you're looking at the address. Still about
you specify the address of where you want to be. What is the
Yeah, basically,
which means you can actually specify that number instead of ampersand. It will work the same way too.
Just question. The addresses given are not like constant registers, right? It's just some type of name we use.
Hold on a second. Let me.
Because in memory, when the application